afternoon, everyone. We are in the week 6 problem solving session of the NPTEL course, Network Analysis. And week 6 is about circuit analysis with Laplace Transform. Let me share my screen. I hope you are able to see my screen. So only this week, this session will be on Saturday 4 to 6. But from next week, that is week 7, it will be again from Monday 6 p.m. to 8 p.m. Due to my unavailability on this Monday, I have preponed it so that people who are available can attend this session, else they can go through the video because it will be uploaded by that time. Okay. So week 6 is about circuit analysis using Laplace transform. So this entire week is about Laplace transform, how we can use Laplace transform in series RLC network, and how to get the solution for series RLC network using Laplace transform. So yeah, the heading of today's discussion is circuit analysis with Laplace transform. So before we go into how to solve using Laplace transform, I just want to explain like what are the advantages of using Laplace transform. So yeah, the advantages of Laplace transform. There are two main advantages, and also why we are using this, because it will make our job easy when we solve any RLC network. So yeah, the first advantage being whatever differential equation, if we consider any networks that we have solved in the past weeks, we have seen that first we need to get the differential equation, and then we are solving the differential equation by means of solution or phasor method or any other method. So using Laplace transform, all the differential equation will be converted to algebraic equation. So there will be no differential term. So it will be just like any DC steady state RLC network which have current and voltages and impedances. So there will be no d by dt term or integral term. So it will be very easy for us to solve. It will be just like any other algebraic expression. Yeah. So all the differential equations will be converted to algebraic equations. Okay, this is one advantage. The second advantage is if you see solving any differential equation using the solution, we have understood there are two parts. One is the homogeneous part, and the other one is the no, natural response. Other one is the forced response. So we have two kinds of responses. We'll first solve for natural response, which is because of the initial condition, and then forced response because of the input. Later, when we were using phasor, we were only trying to get the forced response, not initial condition. So it is removing the transient part, and we are only getting the solution at the steady state. But if we want both steady state as well as transient, then we need to solve the differential equation, which we have realized it is very lengthy and is also very complicated. So using this Laplace transform, we can get both the transient as well as steady state at a time. So both transient and steady state solution or can be obtained at a time. So these are the main advantages, and it also makes our life simpler when we are solving any equation that will be seen within few minutes, can be obtained at a time. So now we'll see if we convert our normal time domain to S domain. So when we say Laplace transform, it means it is in S domain. Okay. So first we'll see RLC circuits and how they are transferred in the S domain. So I am considering I hope you are following. I'm audible, right? Can anyone please confirm? Yes. Okay. Thank you. So we are considering RLC in S domain. So for any given circuit, first we have to convert whatever circuit they have given into S domain, and then we'll solve the S domain circuit normal, how we solve any other normal circuit. And after solving in S domain, then we'll again convert it into T domain. That is a different part. We'll slowly see that. So first I'm considering a resistor. Sorry, it's a resistor. Okay. So I'm considering a resistor with current I of t, voltage V of t, and R. So in the time domain, so if I write two headings, one is say time domain expression, another one is S domain or in the Laplace domain, S domain expression. So we'll be having in time domain, as you know, V of t is equals to I of t into R. So now if we apply Laplace transform on both the sides, say V of t is V of s, I of t is I of s. So what we'll be getting here? Anyone? Times R. So for resistor, the S domain of the R equivalent or the equivalent term of R in S domain is still R. Whereas in the case of other components like capacitor and inductor, if we consider say inductor now, we have I of t, inductor L, and voltage is V of t. So now in the time domain, we have V of t is equals to what? L di by dt, right? L into di of t by dt. So if we apply Laplace transform of any function, so here I'll give you a formula. So the formula is say f of t as Laplace transform f of s, then df by dt will be having s into f of s. So this is a formula which you can derive using the Laplace transform. But all these formula you need to keep in mind, and you need not always derive, and you should not also derive every time because these are very well known results, and these are to be remembered. So you need to remember all these results. So that table also I'll be giving, so you can go through the table. So all these results you need to remember so that you can quickly solve any problem. So now if we apply Laplace transform of this, we'll get S into I of S. So on the RHS side, we'll have V of S is equals to S into I of S, right? So I'll segregate I of S term once and S terms in the other side. So now for inductor, we have I of S into SL. Now we'll get back to capacitor. So say capacitor is like this. Now we have current I of t and C is the capacitance and plus minus V of t. So we know that in time domain, we have I of t is equals to C dV by dt, right? Now in the time domain, what it will be? C into dV by dt in Laplace transform. If you apply Laplace transform, it will be S into V of S because we have seen from this formula. So for di by dt, it will be S into I of S. For dV by dt, it will be S into V of S. So now if I bring all the terms on the left hand side and keep only V of S in one side, we'll get V of S is equals to I of S into 1 by C into S or SC, whatever way you want. C into SC. So now if you see in the time domain, we have all these d by dt terms. So for us to solve, we need to go by that solution method, a linear differential equation solution method, which will be difficult. Now we have converted this into a particular domain called S domain by applying Laplace transform. And you can see that these both, like if you consider these two are same, but the advantage of the S domain is we have V of S and I of S relation by just some constant with some additional term S. So now I can treat this entire inductor as it is having some impedance SL and IS is flowing. So it's like voltage is equals to current into impedance. So what I mean to say is, so in the S domain, we have something like voltage is equals to current times impedance. And the impedance for resistor is R, for the inductor is SL, for the capacitor is 1 by SC. So it is just very simple, and we can directly use that formula or the S domain representation, and we can solve any circuit quickly. So, uh, just to quickly write, we have R, we have L, we have C. So if we write them in the S domain, R is still R, whereas L is SL and C is 1 by SC. So now any circuit with RLC, I can replace it with R, SL, 1 by SC. Then I'll solve as if voltage is equals to uh, this current into impedance, and then I'll get whatever current I want in S domain. And after solving, then I'll convert into time domain. So the steps are as follows. So for any given circuit, maybe I'll steps to solve a given circuit. Okay. So the first step is any given circuit, you have to apply Laplace transform and write everything in Laplace domain. So convert everything into S domain. Now we have converted everything into S domain, voltage, current, the resistor, inductance, all the impedances, everything. Now we'll solve them algebraically. Now you can apply nodal analysis. Now you can apply mesh analysis, or you can apply Thevenin's theorem or Norton's theorem or any other theorem, and you can treat it as a normal simple circuit. So now you solve the circuit using any analysis. So it will be just like an algebraic solution or algebraic equation. So you have to solve the circuit in the S domain itself. Okay. Now in the third part, I'll use a different color. After getting, say, they're asking current in particular branch. I have solved the current in that branch. So now I got I of S, but I need I of t. So we apply Laplace, inverse Laplace transform and get back into time domain. So now apply inverse Laplace transform. So the idea is basically very simple. We are using something called Laplace transform to solve the elements or any given circuit in a much simpler way, so that it will save our time. Also, it will be easy for us, and it will reduce a lot of differential equation calculation and complicated terms. So it will be easy from our side also. Also, it will save a lot of time. Now, in order for us to solve in the S domain, first we have seen R, L, and C. In S domain, will there be any change? In resistor, of course, there is no change. Whereas in the case of L, it will be SL. Whereas in the case of C, it will be 1 by SC. Now, this can be represented as voltage is equals to current times impedance, where this impedance is given by R, L, SL, and 1 by SC. This is in time domain. This is after applying Laplace. So Now we have basically started with R, L, and C. So if any given circuit has this RLC network, first we'll convert everything into S domain. Then we'll solve the circuit in S domain. Then we'll apply inverse Laplace transform to get the time domain solution. So this is when RLC are not having any initial conditions. So this is without any initial condition. I hope you are following because no one is answering. Are you following? And are you understanding?
Yes, sir.
Okay. And when is the deadline for week 6 assignment submission? Hello. Wednesday. Okay, fine. I'll try to upload this video by tomorrow night or maybe tomorrow afternoon so that you can access it. Okay, Wednesday. Yeah, thanks for confirming. Now we have seen RLC without any initial condition. Now with initial condition, register, there is no initial condition because it doesn't have this, it is a like non-memoryless element, right? So for resistor, there is no question of initial condition. So for inductor and capacitor, there might be initial condition. So resistor, it's just again V of S equal to I of S into R. It does not have any memory. So there is no initial condition. So now with initial condition. So let me consider an inductor. L and I of t and voltage is V of t with initial condition say I of 0. Now this I can represent it as inductor with no initial condition having a current source in this way, whereas this is I of 0 and this is the inductor current, the overall solution with considering the initial condition, and inductor value is L. This is plus minus V of t. So now first with the given inductor current, we have represented it in a way that the initial condition is represented as a current source because now I of t will be, so now I of t will be this part plus this part. So I of t is initial condition plus the solution of inductor without initial condition, which is also same as this. So we are considering inductor with initial condition to be initial condition separated with inductor without any initial condition. So we have just separated out that initial conditions. Now if we do the Laplace part of this one, we'll have something like this. So we know that inductor can be represented as SL. So we'll represent it as SL. Also, let me draw this initial condition. Okay, now this will be I of S, this will be SL, this will be plus minus V of S. And for a constant K, Laplace transform is K by S. So for I of 0, it will be I of 0 by S. Okay, so with uh, initial condition, if there is any inductor and say the initial condition is I of 0, it will be replaced like this, the inductor having SL with initial condition I of 0 by S. So this is the correlation between time domain and Laplace domain. Similarly, we consider a capacitor with the initial condition. So these are the two terminals. Okay, this is I of t, capacitor C plus minus V of t with the initial condition V of 0. So inductor is having current initial condition, capacitor is having voltage initial condition. So current will be added, right? Initial condition plus the normal solution. So when we are trying to add currents, so the current will be having a branch, another branch, because for current we'll apply what? Nodal analysis. So if the current is, you're dividing the current into two parts, then that those two branches, I mean to say this branch, this first branch and this second branch, they will be in parallel, because then only the currents will be added. Here in the case of capacitor, we are separating the voltages and we are adding the voltages. So when you are trying to separate and add the voltages, it will be series. So current, it will be parallel, whereas in the voltage it will be series. So I hope you understood what logic I'm trying to do here. Here current has two parts, initial condition plus normal solution. Overall solution will be a combination of these two. So that's why current is being divided into two parts, which can only be done if they are in parallel. If they are in series, it is the same current. Whereas in the case of capacitor, it has two voltages. One is the initial condition, the other one is the normal solution. And we need the summation of those two. And as these are voltages, they need to be connected in series. So the polarity is actually very crucial. So the current is flowing in this direction, so plus minus will be in this direction. Maybe I'll use a different color so it will be noticeable. So now we have again I of t with the capacitor having no initial condition in series with a voltage source V of 0, which is like an initial condition. And the overall thing is plus minus V of t, the overall solution, because we are considering the overall voltage to be divided into a voltage plus a capacitor without any initial condition. So we have to be careful with that voltage. So the overall voltage is V of t, because we are just representing this, we are just representing this capacitor as this thing. So it is just the same thing. So the overall voltage is V of t. Now I can write this as this, and we have plus minus. Okay. So I of t is I of s. C is 1 by s into c plus minus v of s. This is plus minus. And v of 0 is a constant, right? Laplace transform of the constant is v of 0 by s, because for constant, Laplace transform is 1 by s. So until this point, is it clear? So we have discussed how RLC can be represented in S domain, so that we'll directly use these results and no need to derive it again. It is very simple. Resistor is resistor, inductor is SL, capacitor is 1 by SC. And then we'll convert it to S domain, and then we'll solve in S domain. Then we apply inverse Laplace transform to get in time domain. Whereas if there is an initial condition, we'll add a parallel path if it is an inductor, or a series voltage source if it is a capacitor. And the polarity is very crucial. So as this side is plus, so it will have V of t will be initial condition plus this voltage. So the polarity of the voltage is very crucial. You need not should not make any mistake while choosing that polarity. So is this clear until this point? If you have any doubts, you may ask. So we'll solve a quick problem that I have taken from the lecture notes. This lecture notes. So whatever I have shown, it is just the same thing I have taken from this notes. So we'll quickly solve one problem. Yeah, this problem. I hope you are following. And if you face any difficulty, please stop me at this point only. So we have this question, and they are saying, given the capacitor voltage, initial voltage is minus half, redraw the circuit in S domain and calculate I of t for t greater than 0 when the input is V in is equals to t for t greater than or equals to 0. Okay. So this is our problem one, or maybe I'll just take this a bit down. Okay. So this is our problem one. So they have given A capacitor with initial condition, inductor is not having any initial condition. And they have also given V in of t is equals to t for t greater than or equals to 0. So initially it is 0, and initially the capacitor voltage is minus half. Now a source of value t is applied. Now they are asking what is the I of t, right? They are asking I of t. So we have to calculate I of t. So the method is simple. First, we need to convert everything into S domain. Okay, let us convert it into S domain. So resistor is, first let me draw, then we'll write the S R L, then capacitor plus capacitor initial voltage, initial condition. Now the source. Okay. Okay. Now I'll write the S equivalent. I of t is I of S. V in of t is, say, V of t, V of S. What is the value of V of S? That will come back after completing the circuit. So resistor is resistor only. So it is 1. What will be inductor? L value is 0.5. So in the S equivalent, what will be the value? Anyone? Inductor is
Sir,
L.
S by 2.
S by 2. Oh, yes, you are right. So, or 0.5 S if I want to write. Okay. And C, the value is 1. So, what will be in S domain?
1 by S.
1 by S, you are right. And this initial condition is minus 0.5. So, what will be the value in S domain?
Sir, minus 1 by S. 1 by
Minus,
2S.
yes, minus 1 by 2S. Now we have converted everything into S domain. So our first part is done. Now we have to solve the circuit in S domain. So now there is no d by dt term. Nothing is there. We just have to apply our mesh analysis, nodal analysis, anything. So here V of S. So if this is V in of t, we'll come back to this table. What are the results of Laplace transform? I'll come back to that. But for the time being, you just believe that V of S, if V of t is t, V of S is 1 by S square. You know this, right? I'll also come back to that table, so you can quickly refer to that table. Okay. So now in this problem, if I apply KVL in this loop, and if I start from this ground, I'll be getting what? I'll be getting V of S minus R plus 0.5 S plus 1 by S into I of S minus of minus 1 by 2S is equals to 0. Do you agree?
Yes, sir.
Yes. So now I'll substitute this part here. So I'll be having, and again R is 1, so I'll have to replace this by 1. So R we can replace by 1. So it is 1 plus 0.5 S. So now after replacing this, we'll have 1 by S square plus S by 2 is equals to 1 plus 0.5 S plus, sorry, I think this is 1 by 2S, not minus S by 2. Again, I have made a blunder. So S is in the denominator. So here also S will be in the denominator. 1 by 2S. So 1 plus 0.5 S plus 1 by S into I of S. So now everything is in S domain, and I of S we can directly calculate. So I of S is equals to I of s is equals to this LHS will be s plus s plus 2 by 2s square, isn't it? So I can multiply this by s, and here I can write s square, here I will write 2s square. So it is s plus 2 by 2s square, right? Okay, I hope you are also calculating. So this will be coming in the denominator. So it will be s by 0.5 s square plus s plus 1. Okay, you check the calculation. I might be doing mistake, so you have to correct me if I make a mistake. So this SS will get cancelled. Now we'll be getting s plus 2 upon s square plus 2s plus 2, isn't it? Just check the calculation. I hope you are also doing with me. Don't just assume that whatever I'm doing is right. It could be wrong as well. So you just check what I'm doing. So here v of s I have substituted 1 by s square and plus 1 by 2s. So if we add these two, we'll get s plus 2 by 2s square. And then I have brought this term in the denominator. So it will be inverted s by 0.5 square plus s plus 1. Now I have multiplied by 2. So it will be s plus 2 by s square plus 2s plus 2. Is this okay until this point? Hello.
Yes, sir.
Okay. Now I'll rewrite this I of s. Okay, I have missed this term. So there will be one additional s also. We have not pointed it out. So our I of s is s plus 2 upon s into s square plus 2s plus 2. Right now we have to use the partial fractions that we have learned. A by s plus bs plus c by s square plus 2s plus 2. S square plus 2s plus 2 is not having real roots because b square minus 4ac is less than 0. So it has imaginary roots. So it cannot be factorizable. So the denominator will be as it is. So we have s term. So numerator will be constant. And here the denominator is second order. So numerator will be first order. Now we have to solve for a, b, c. So just let me take this to the next page. So this is our I of s. Okay, so with this I of s, now we have to calculate I of t. So for that, always, if there is any such numerator by denominator expression, so we are still in part 2, right? So part 2 is just convert the circuit in S domain. We have converted and we got the expression. Now we have to apply inverse Laplace transform. But before applying inverse Laplace transform, we have to convert this into subterms so that we can apply inverse Laplace transform easily, because there are some results that we need to remember, using which we can directly apply inverse Laplace transform. So if you calculate the numerator here and the numerator on the LHS side as well as numerator on the RHS side. On the LHS side, we have s plus 2. On the RHS side, we have as square plus 2as plus 2a plus bs square plus cs. So if we consider s square term, there is no s square term. So a plus b is equals to 0. Now I'll consider s term, s term, s term. 2a plus c is equals to 1. Now I'm left with only one term, which is the constant. So 2a is equals to 2. 2a is equals to 2. So a is equals to 1. Now you substitute this in this equation. You will get c is equals to -1. You're also doing right with me, along with me.
Yes, sir.
Yeah. So now if we substitute, B is also equals to -1. So now we got A, now we got B, now we got C. We'll back substitute all these equations in this to solve I of S. Now I of S is nothing but 1 by S, right? A and B is -1, C is -1. So I'll subtract, I'll take the minus common. Numerator will be S plus 1. Denominator we'll write in a form s square plus 2s plus 2 as s plus 1 whole square plus 1 square. I'm just reframing it in a way that it will fit into my result. I'll again tell that result. So now we have to apply inverse Laplace transform. Okay. So after applying inverse Laplace transform, you will get I of t is equals to 1 by s. Inverse Laplace transform is 1 minus. For this term, we can write it as e to the power minus t into cos t. We'll get to that part how it is being written. So how I'm writing, it is just a result again. So using that result, we can directly do. But for the time being, assume that we know that result into I of t is for t greater than or equal to 0. So u of t with the initial condition. So this is our overall solution. So if you see, we have just converted everything into S domain, then solved it algebraically. After solving it algebraically, we have just got this I of S expression, and then we have used partial fractions concept here. So we are converting into few fractions, and we have assumed unknown constant ABC. Then by comparing LHS with RHS set, we have obtained ABC. Then by back substituting those equations here, then we got IFS expression. Then we have applied inverse Laplace transform to get I of t. So this is which is what I think they are also getting 1 minus e to the power minus t cos t u of t. So we have realized the advantages of Laplace transform. So it makes our life simpler, and also we have to keep in mind that it is just any other circuit. First we'll convert into S domain, then you can apply any analysis. So you can apply nodal analysis, you can apply mesh analysis, all other theorems that you know, all are valid. Superposition theorem, you can apply Thevenin's theorem. You can apply Norton's theorem. There is less than a minute, so if this meeting can kindly join back, then we'll go to that Laplace transform results table, which we have to memorize so that we can solve the answers or solution quickly. All are applicable. So in S domain, all are applicable. So we are only converting into some domain where things are much simpler and everything can be solved just like any other circuit. And then we have to apply inverse Laplace transform. So I think this meeting will end. After that, we'll go to that Laplace transform table. If you have any questions, you may ask at this point. Okay, so we'll get into Laplace transform table. So first of all, the Laplace transform for any function f of t is say function is f of t, then the Laplace transform of that function f of t can be represented as f of s. So say function is f of t, and its Laplace transform is f of s. Now f of s can be written as, so usually in time domain the notation is small letters, so small f, and whereas in the case of S domain, usually it is capital letter. So that is the convention everyone follows. So it is expected that you also follow as you are in the learning stage. So f of s is integral what, 0 to infinity f of t e to the power st dt, right? Hello.
No, sir. The integration limit is minus infinity to infinity, no, sir.
Yes. Or others? What is the integration limit? 0 to infinity or minus infinity to infinity? Hello, anyone?
Sir, minus infinity to infinity.
No, you're right. So now we'll get back to f of t. Say we have so I have written some functions. So from there, I'll just take a note. First function is 1. So if it is a constant 1 or k, it will be 1 by s, simply. And if it is, say, t to the power n, so it will be n factorial by s to the power, or maybe I'll write in the other way. So this is 1 by s. This is n factorial by s to the power n plus 1. Okay, I will not be going into the derivation because these are well-known results. If you substitute here, you will be getting that expression. So now it is sine of at. Sine of at is a by s square plus a square. So sine t will be 1 by s square plus 1. Similarly, cos t, if we get, you'll get s by s square plus a square. Now if we, sorry, not cos t, cos at. Okay. Now if we go to e to the power at, in the s domain, it will be 1 by s minus a. Are you following?
Yes, sir.
Yes.
So now if I combine one trigonometric term as well as exponential term, say e to the power at cos bt. So now for cos bt, it will be s by s square plus b square. But if there is an exponential term e to the power at coming, then you have to replace s by s minus a. So this will be s minus a by s minus a whole square plus b square. Similarly, if we do the same for sine, we have e to the power at sine bt. It will be s. Now we have to replace it by b. So b, because the numerator is b here. cos sine bt by denominator is s minus a whole square plus b square. So if we just go back to our previous equation, it is s plus 1 by s plus 1 whole square plus 1 square. So our a is minus 1. So our a is minus 1, b is 1. So it will be e to the power minus t cos t. So that is how we have written. Whereas if you want to do inverse Laplace transform, it is very difficult. That's why we remember these results and we'll use these results because will be getting all the equations in any one of these Laplace domain or time domain. So it is expected or it would be advised you remember all these things. Now, if our function is integral 0 to t f of t dt, then in the S domain, it is f of s by s. So if the term is integration, then we'll get 1 by s. Now we'll take convolution. So our input is having f of t convolution g of t. So this is not multiplication. This is convolution. Now in the S domain, it will be f of s times g of s. Now, what if I take in time domain f of t times g of t? So this is multiplication and this is convolution. So in the S domain, we will get f of s convolution g of s. So it will have that duality principle. If the convolution is in the time domain, it will be just product in S domain. If the convolution is in the S domain, it will be just product in time domain. Okay. Now there is this final term f and t. So this is like the nth derivative. Okay. So nth derivative will have this expression s to the power n f of s minus s to the power n minus 1 f dash of 0 minus s to the power n minus 2 f double dash of 0 plus up to 1 minus f to the power n minus 1 0. So this is the term for the nth derivative. So if there is second derivative of f of t, we'll have up to this second derivative term. If it is nth derivative, then we'll have up to n minus 1 derivative. Is yeah, it is fine. So it starts with s to the power n and s to the power n minus 1 up to so on. It will go to s. Is that clear? Hello.
Yes, sir.
Yes. Okay. And one more thing, I'm not sure about this thing. I'm thinking it should be 0 minus. So you just check this part, whether from where it is starting. The integral, I'm thinking it starts from 0 minus. You just check once. I'll also update when I'll upload these notes there. So I'll check. You also keep this in mind.
Sir, when the term ut is multiplied with ft, then this sir integral changes, na sir.
Sorry.
Sir, when the
Uh,
function ft is multiplied with function ut, step
yes.
function,
Mhm.
sir, I think then this integral changes to 0 to infinity.
Okay, okay. That part I'll just let you know because it's a formula. I'm probably that I'll check. I'll check and I'll get back to you.
Okay, sir.
So till now we have discussed the circuit analysis with the Laplace transform, the basic advantages and how to solve. What are the steps with initial condition? What are the like if we convert them into this kind of S domain with the initial condition as well as initial uh, without initial condition. What are the equivalent circuits? Then we have quickly solved one problem, followed by the Laplace transform table. And I'll check this and I'll get back to you. By when I upload this, I'll make sure that I'll modify in these notes and then only I'll upload in the YouTube. Okay. Now we'll quickly solve one problem. So let me go back here. So we'll solve assignment 6. But yes, these are also like it could be tricky if you are making any mistake, then there is a possibility that you might end up making some mistake. So you should be very careful when you are doing this. So this is our question, the first question. Okay, so we'll read the question now. The first question says the switch is closed at t equals to 0. Before that, the capacitor was charged to Vc of 0 minus is equals to 15 volt, and there was no current through the inductor. Now, for t greater than or equals to 0, they are asking what are these currents as well as the capacitor voltage. So they're asking what are these constants. So first we need to solve. So we'll solve for I1 of s, I2 of s as well as Vc of s. Then I will convert them into the time domain. Okay. So now this is problem number 2. Okay. So first part is converting this into S domain, right? So we have to convert this into S domain and then solve it as it is. So if we convert this circuit into S domain, how we'll be getting? After t equals to 0. So here we have the inductor, here we have the resistor, here we have initial condition for the capacitor, and then the capacitor itself. Okay, so this is 42S and this is 222. And what is the capacitor? 1 by CS, right? So it will be, what is the value? Hello, for the capacitor. Anyone? Hello.
3108 divided by S.
Yes. 3108 by S. And this is plus minus. And the voltage is 15 by S. Because the constant value is 15. And now this is I1 of S. This is I2 of S. And the overall voltage is Vc of S, as we have discussed, because the initial condition will also come into the picture. Okay. So now this is the overall expression. So let me just copy paste it. Control C, Control V. So now we have this thing. Now we'll solve for the currents I1, I2 as well as Vc of S. So we'll first, so how are we going to proceed with this? Anyone? So what are your initial thoughts? Say we have given this circuit, so what could be, like how we should proceed?
Kirchhoff's current law.
Sorry.
We should use Kirchhoff's current law.
Kirchhoff's current law. That is one thing. Yeah, and yeah, mesh analysis also you can do. Anything you can do. But I believe like my way of solving is we can combine these two. So then we'll get an equivalent circuit. Then we can directly apply voltage by the net impedance. So what I mean to say is I'll which is also again KCL because there you'll be getting two equations and then finally if you convert that into one equation, you'll be getting like this. So I am saying I'll replace this by an impedance with a voltage source plus minus followed by the capacitance. So now this is I of S and this is some impedance Z and this is 15 by S and this is 3108 by S. So now voltage is current multiplied by the total impedance. But before the total impedance, what is Z? Z is 42 into S multiplied by triple two by 42S plus triple two, right? These two things. Is this right?
Yes, sir.
Okay. Now my I of S is V of S, which is 15 by S multiplied by 1 by Z plus 3108 by S. Okay. Now I'll substitute this Z in this expression. So now I'll write my overall I of S. My overall I of S is 15 by S multiplied by 1 by 42S plus, sorry, 42S into 3/2 into 3/2 by 42S plus 3/2 plus 3108 by S. So this is how we'll be getting. Now, if we further simplify this, we'll get 15 by S. And if I'm making any mistakes, kindly let me know. So 15 by S in the denominator, we'll have 42 into 222 S square plus 42 into 3108 S plus 3108 into 222. In the numerator, it will be 42S plus 222 into S. And this SS gets cancelled. So our final I of S is equals to this part. 42 into 222 S square plus 42 into 3108 S plus 3108 into 222. And in the numerator, we'll have 15 into 42S plus 222. Okay. Now we got I of S. Now we have to calculate I1 of S and I2 of S. So what is the relation between I1 of S and I of S? What is the relation? I1 of s, I2 of s.
Sir, current division.
Yes, current division. So I1 of s will be this impedance triple two by summation of these two into I of s, right? So I1 of s is equals to triple two by 42s plus triple two into I of s. So if we do that, we'll be getting, let me take this video to the top. We'll be getting I1 of s is equals to, so this term denominator will be cancelled with this numerator. So we'll be left with 15 into triple two in the numerator. So it will be 15 into 222 by 42 into 222 s square plus 42 into 3108 s plus 3108 into triple two. Yes. So we'll be getting this kind of expression. Okay. Now let me just add a new page and take this equation there. So there we'll apply the inverse Laplace transform. Okay. And now this is I1 of s. Now we have to also similarly calculate I2 of s. But first let us solve for I1 of s and then we can go for I2 of s. So what I'll be doing is in any of our formulae, if you see, s coefficient is always 1. So first we have to make s coefficient 1. So we have to divide by 42 multiplied by triple two in the numerator as well as denominator. And I have already calculated it previously so that I will not make any mistake during this class. So you also check with me. You also do the calculations. So after multiplying or dividing in the numerator and denominator by 42 into triple two. So divide by 42 times triple two in numerator, comma, denominator. Then we'll be getting something like this. So you also do along with me. So in case if I make any mistakes, you can correct me. So I got something like this 0.357 by s square plus 14s plus 74. Yeah, so I got something like this. Can you please check and confirm whether you're also getting the same thing? Just divide by 42 into triple two in the numerator and denominator. So you will be getting something like this.
Yes, sir.
Okay, okay. Yeah, thanks for confirming. And if you see the denominator, whether the roots are real or imaginary. B square minus 4ac, whether it is greater than 0. So B square is 196. 4ac is 4 into 74. So 4, 4, 16, 4, 7, 28, 296. So 186 minus 296. So delta is less than 0. So imaginary roots. So if the roots are real, then we can get in lesser order, like S order, I mean first order. Whereas if the roots are not real, then we'll have to convert that into in this domain. So there will be cos sign terms. So now we have to convert this into something like this. So this is S square. If this is 2ab, it will be 2 into 7 into S, right? So a square plus 2ab plus b square. So a square is s square, 2ab is 2 into 7 into s. So, and now what is b square? 7 square, 49. And if you remove 49, you will be end up with 25. So the denominator can be written as s plus 7 whole square plus 5 square, isn't it?
Yes, sir.
Yes. Now, if this is the denominator, there are two possibilities for the numerator. One is for the cost term, one is for the sine term. For the cost term, you need to have s in the numerator. We don't have that. So the only possibility is this sine term. So for the sine term, you need to have b in the numerator. So b is what? 5. So I'll write 5 here, and then I'll divide by 5. And I'll write the remaining term, which is 0.357. Okay, so now my I1 of S. So what is 0.357 by 5? It is 0.0714. 0.0714 into 5 by S plus 7 whole square plus 5 square. We got something like this, right? You also check the calculations. So now if we apply inverse transform, we know that this is nothing but e to the power minus 70 sine 5t. So now we'll be getting I1 of t as 0.0714 into e to the power minus 70 sine 5t, isn't it? I1t. So we'll go back to our question. So u of t. I1 is constant into e to the power minus kt sine omega t plus 5 u of t. So yeah, u of t will be there because we are doing for t greater than 0. Then yeah, Neeraj, you are right. So we have to consider u of t. So then it will be 0. Yes. So instead of writing this, I'll write something like this. So create, it will not create any issue. So for function f of t, u of t, then we'll be having 0. Yeah, you are right. Now this terms will be integral 0 to infinite. So for t greater than 0, we are considering the function. So u of t we are considering. Now, as u of t is only 1 from 0 to infinite, the integral will become 0 to infinite. Okay. Now, if we come back here, so this is my I of t, or I1 of t to be precise. So my I1 of t. So I'll check with the calculations whether uh, it is properly matching or not. So I'll go back to this question. So I1 is A1 and Phi1, right? So A1 is 0.071. So it is within the range. And my Phi1 is 0 because I got sine 5t. So Phi1 is 0. So it is matching. So whatever I1 we have calculated, it is correct. So did you follow until this point how we have calculated I1 of S and applied inverse Laplace transform to get I1 of t? If you have any doubts, we may ask, else we'll go to I2 of t calculation. Any questions? Hello. Hello, Neeraj, Bharat, Kavya Patil, Nia.
Yes, sir.
Okay. So now we'll go for I2 of S. So I2 of S is 42S by 42S plus triple two into I of S. So let me just take this I of S. Let me just copy it. And let me just paste it here. Okay. Now I have to get back to my I2 of S. So my I2 of S will be So my I2 of S is what 42S by 42S plus triple two. 42S by 42S plus triple two into I1 of S. Now, if you substitute this, or sorry, in the other way, this in this, so I of S needs to be substituted, then we'll be getting something like this. I2 of S is equals to numerator will have 15 into 42S and denominator will have 42 into triple two S square plus 42 into 3108 into S plus 3108 into triple two, and in the numerator we have 15 into 42S. So it is something like this. Do you agree? I2 of S. I have just substituted I1 of S. So this term will be cancelled with this term. And we'll have 15 into 42 of S in the numerator and rest of the terms in the denominator.
Okay, sir.
Now, whatever logic we have used previously, that S square coefficient should be 1. So we'll use the same logic. So I'll divide by 42 into triple two. So in the denominator, you divide by 42 into triple two, and in the numerator also, you do the same. Then you'll be getting this expression. So the denominator will be the same, S square plus 14S plus 74. Numerator is 0.0 6756. Just check whether you are getting the same expression or not. So we have just divided by 42 into 32, both in the numerator as well as the denominator. So this is my I2 of S. Did you get it?
Yes, sir.
Okay. So let me just again write this equation quickly in the second page. So now we have I2 of S is equals to 0.06756 S. By denominator again we can write S plus 7 whole square plus 5 square. So now it is in like which format out of these tables, whether it is cos or sine.
Sine.
Are you sure? Because we have S term in the numerator.
Cos format, sir.
Cos format, yes. So we have this in the cos format, but for the cos format, we need S plus A in the numerator. We have only S. So what I'll be doing is I'll be writing S as S plus 7 minus 7. So I'll subtract or separate this term as well as that term. So we will be getting 0.06756 into S plus 7 by S plus 7 whole square plus 5 square minus 0.06756 into 7 by s plus 7 whole square plus 5 square. Now I know immediately that this is like e to the power minus 70 cos 5t. But what about this? What about this term? This is still yet to be modified, because for us to get in this sign format, the numerator should be 5. So what I will be doing, I'll be multiplying and dividing it by 5. So I'll multiply by 5, divide by 5. So now what I'll do, I'll rewrite this expression again. So I2 of S is 0.06756 into S plus 7 by S plus 7 whole square plus 5 square. So this is my first term. Second term will be 0.06756 into 7 by 5 will be the constant. And if you calculate it, it will be 0.094584 into 5 by S plus 7 whole square plus 5 square. So we have just converted everything into the expressions that we know the inverse Laplace transform of. So I know that this is e to the power minus 70 cos 5t, and this is e to the power minus 70 sin 5t. Right? Do you agree? Hello.
Yes, sir.
Okay. Now, what we'll be doing? We'll be writing I2 of t. So I2 of t is 0.067. There is less than a minute, so if this meeting ends, kindly join me. Into cos 5t minus 0.094584 into sin 5t, and it has that e to the power minus 70 term. So now I see that it is in the format of sin omega t cos theta, cos omega t sin theta. So for this to be converted into cos theta or sin theta, I have to multiply and divide it by square root of 0.067 square plus 0.094 square by square root of 0.067 square plus 0.094 square. Understood what I am trying to do here? So we are basically multiplying by square root of this term and dividing by the same term so that the value remains unchanged. So now what we can do is we will consider this term, and we'll consider this term. So this term I'll write as cos theta. This term I'll write as sin theta. And if you calculate the value of this constant, it will be coming around 0.116. So I have calculated it earlier. So it is coming to be 0.116. So I2 of t can be rewritten as minus 0.116 into e to the power minus 70. And of course, there will be u of t term here also, because for t greater than 0. So we'll have into u of t into sin 5t cos theta minus cos 5t sin theta. Whereas theta is given by tan inverse of this value by that value. So you will get tan theta to be 5 by 7. That implies theta is tan inverse 5/7. Okay. Okay. So we have transformed this expression into sine of a minus b. Now we can rewrite this expression as I2 of t is equals to 0.116 into e to the power minus 70 ut sine pi plus 5t minus theta. Why? Because this is responsible for 5t minus theta, and this minus is responsible for this pi. Sine pi plus theta is minus sine theta. So minus of sine theta is sine of pi plus theta, or pi plus some value theta 1. Here theta 1 is 5t minus theta because it is coming from sine a cos b minus cos a sine b. Now I will rewrite this expression as something like this. I2 of t is equals to 0.116 e to the power minus 70 ut into sine of 5t plus pi minus theta. I will replace theta tan inverse 5/7. So this is the final overall expression that we are getting for I2 of t. Okay, so this is the overall expression that we are getting for I2 of t. So what, to summarize, from the I of s, we got the I2 of s expression, and then we have realized that the numerator s means it is in cos thing. So we have added plus 7 minus 7, and we have segregated both the terms. So we have realized first term is for cos and second term is for sine. Then these constants we have replaced it by sine theta cos theta. In order to do that, we have multiplied by square root of a square plus b square, so that this term is cos theta, the other term is sine theta. And then we have calculated tan theta by this constant a by b. So theta is tan inverse a by b, which is here 5/7. If you calculate, you'll be getting. Then we have calculated I2 of t and made some mathematical manipulations to get it in the way that they have provided in the question. So now here A2 I know, phi 2 also I know, and omega also we know. So A2 is 0.116. So we'll see A2. A2 is 0.116 in this region. And phi 2 you need to calculate it. If you calculate the phi 2, here we have pi minus tan inverse 5/7. So you calculate that, you'll be getting some 2.52 radians. Again, phi 2 is in radians. So you have to be careful. Phi 2 are in radians. So this is very crucial. So if we go back, these are the things that you might be doing mistakes. So one thing is these are radians, and another thing is they should be from minus pi to pi, because any theta is equivalent to 2 pi plus theta, 2 pi minus theta. So there are n number of solutions, right? So phi 1, phi 2, phi v or phi e, whatever they're saying, they should be within this minus pi to pi range, and also they should be in radians. So our value is pi minus tan inverse 5/7, which is less than pi, of course, and it will be 180 degrees minus tan inverse 5/7 degrees. Then in order to convert to radians, you have to multiply by pi by 180. So I think you'll be getting 2.52. Let me check. 2.52. So phi 2 you'll be getting 2.52. So here we have calculated I1, I2. So now VC of t. So VC of t, what is VC of t? So VC of t, here VC of S, say, is nothing but, so in this expression, if you want to say VC of S plus minus VC of S, I can say this is also plus minus VC of S. So our VC of S is nothing but I of S into this net impedance Z, right? So where is my I of S? This is my I of S, right? So I'll take this. Okay. So are you following what I'm trying to do here?
No, sir. Please repeat the last
Okay.
step.
Okay. So they have also asked us to calculate what is so they have asked us to calculate what is VC of S. In the beginning, I have told that the VC of S is across this initial condition term as well as the capacitance term. So VC of S, if you come back here, so VC of S is nothing but this overall voltage. Now we have transformed this into this circuit. So VC of S is nothing but this. VC of S is nothing but this term. So from here to here, right? Which is
Okay.
also equivalent to this voltage because they are the same terminals. So VC of S,
Yes.
I can write it as Z into I of S. Right. So I know Z. Z is what? 42S into triple two by 42S plus triple two. So I have to multiply this Z term into the obtained I of S term. So I think I have previously copied I1 of S. So let me just copy I of S. So were you able to understand now, Neeraj?
Yes, sir.
Okay. So by mistake, I have copied I1 of S. So let us delete this and then paste I of S. Okay. So now we have I of S term. Now we have I of S term, and we also know that Z of S is 42S into triple two by 42S plus triple two. Okay. Now we also got that VC of S is I of S into Z of S. Okay. So now if we do that, we'll be getting VC of S is what? So this 42S will get cancelled. Numerator again we'll have this term 15 into 42 into triple two. So VC of S is nothing but first we'll write denominator 42 into triple two S square plus 42 into 3108 into S plus 3108 into triple two. And in the numerator, we have 15 into 42S into triple two. So is this clear how we are getting VC of S? We have just multiplied I of S by Z of S to get the overall expression. Hello.
Yes, sir. Yes, sir.
Okay. Now, again, we'll do the same thing. S square coefficient will make it 1. So you divide it, the numerator by 42 into triple two, as well as divide by the denominator by 42 into triple two. So now the numerator has 15s term. So the denominator is s square plus 14. So again, we'll directly make it because we already know what is the denominator. S plus 7 whole square plus 5 square. And the denominator, this will be cancelled. This will be cancelled. We'll have 15s, right? Now I'll do the
Yes.
same thing what we have done. 15s, I'll write it as s plus 7 minus 7. Now we'll have VC of S is equals to 15 into S plus 7 by S plus 7 whole square plus 5 square minus 5 by S plus 7 whole square plus 5 square into 21. So I have just written in a way so that we know this term is e to the power minus 70 cos 5t. This term is e to the power minus 70 sin 5t. So I'll just skip few calculation terms because you know why we are dividing and multiplying. So I'll do the same thing, but I'll just skip. If you have any queries, you just ask me. So VC of t. So VC of t is square root of 15 square plus 21 square e to the power minus 70 into 15 by square root of 15 square plus 21 square cos 5t minus 21 by square root of 15 square plus 21 square sin 5t. So what we did, we have multiplied and divided by the same term. So now I can write this term as cos theta, and I can write this term as sin theta. Now what is tan theta? Tan theta is 15 by 21, which is equivalent to 5 by 7. So that implies theta is tan inverse 5 by 7, similar to what we got in the earlier case. So that's why I'm just uh, going a bit faster so that we can solve another problem. So what we did, we have just segregated it or separated this into two parts. One is giving rise to sin theta, other one is giving rise to cos theta. So now if I write Vc of t, again there will be u of t term here because it is for t greater than 0. So now our Vc of t is minus 15 square plus 21 square, it is 25.806. 25.806 e to the power minus 70 ut sine of omega t minus theta, whereas this theta is this theta. Now I can write the same thing. Considering this minus, I can write pi plus this sine term, right? So now our Vc of t can be written as 25.806 e to the power minus 70 sine pi plus omega t minus theta, because this minus is written as this sine of pi plus theta into u of t. Now the overall Vc of t can be written as Vc of t is equals to 25.806 e to the power minus 70 sine of omega t is what? Omega t is 5t, right? Sine omega t, I'm writing 5. So this omega is nothing but 5 here. This omega is also 5, sine 5t, right? So sine 5t plus pi minus theta. Theta is tan inverse 5 by 7. So this is my overall expression for Vc of t. Now I'll just go check whether it is in the given range or not. Okay. So we see the constant we are getting 25.806. So AV is 25.806, it is lying, and 5V is pi minus tan inverse 5 by 7, which is same as the previous I2 term also. So it will be again 2.52 radians, 2.52 radians. What is K? What is omega? K is exponential term, e to the power 7t, and omega is 5. So K is 7, omega is 5. So K is 7, omega is 5. So it is matching and all our calculations are right. So let me just quickly summarize what we have solved in this problem 2. So problem 2, they have given one RLC network with C having some initial condition. We have followed the 3 steps that we have learned at the beginning, converting them into S domain. After converting them into S domain, we have to solve in S domain, which is the second step, followed by the third step, apply inverse Laplace transform. First, I have converted it into S domain. Then I have just using any analysis you can do. So I have simplified this two parallel things into common impedance. Now I have calculated I of S. Now I know the relation between I1 of S and I of S. Using that relation, I got I1 of S. Because I know that in my inverse Laplace transform or Laplace transform table, that always the denominator coefficient of S square is 1. So I have ensured that uh, this is 1. So I have divided by 42 into 3 both in numerator and denominator, and I have simplified it. Then I have realized it is in the sine term. So I have applied inverse Laplace transform. I got it very simple for I1 of t. Whereas in the case of I2 of t, I have realized it is in the cost term because s is in the numerator. Then I have obtained two separate terms. After getting that separate terms, these are corresponding to these exponential terms, whereas these constants are unknown. So I have multiplied by the square root of a square plus b square and divided by the same term so that I can get this as cos theta sin theta, whereas tan theta is this term by this term, and theta I got tan inverse 5/7. Then I made some mathematical manipulation and simplification. So it will be coming in the format that they have specified in the question. Everything needs to be written in this format. So we have also done the same thing. Then we have compared what is theta, what is omega, and what is the constant. Similarly, for V of t, we have seen that Vc of t is this entire voltage, which is also the voltage across these two things or any individual things. So Vc of t is 222 into I2 of s, or 42s into I1 of s, or I of s into z. So any one of the way you can follow. There are three different paths. You can choose any one of them. I have selected z into I of s path, so which is also Vc of s. So I have multiplied I of s with z of s, simplified. Again, it is cost term. So I separated these two terms, again cos theta sin theta, and then simplified to get the final expression. So until this point, is this clear? It's
Yes,
a
sir.
very like mathematical question. So there are so many calculations, and you have to be very careful at each and every point, else you'll be getting some wrong result. Is this question clear? Problem one. Hello.
Yes, sir.
Okay. So this question is also something similar because here it is in series. So now I have considered this question where they have this mutual term. So this question is also somewhat interesting. So I'll consider this question. So yeah. Probably this question will not be getting entire time to solve, but I'll just show how to get the equations followed by how to solve. I'll just say and I'll wrap up today's session as we are having only 15 minutes of time. So this is our problem 3 for today. So now here you need to follow the steps that we have discussed in the last week, which is how to get these mutual inductance voltage polarities that you need to follow. And the other thing, which is today's thing, first convert it into S domain and then solve. So for your ease, I think I'll open. So it will be easy so that I can correlate what we have discussed in the previous weeks. So sorry, it is week 5, and which is our notes. So we have discussed the polarity, right? Where is the polarity? So we have discussed two cases. One case, if both are entering, polarity will be the same. Other case, if one is entering, one is leaving, polarity will be opposite. So first we'll do this. And here we know that d by dt is nothing but s, because differentiation of any function, if we apply Laplace transform, we'll get s. So we'll get sl, sm, here sm, sl. So keep this in mind. So first, what we need to do, we need to get that equivalent this circuit that we usually draw. So we'll write the voltage sources, and then we'll get the overall equation. Then we can easily solve. So let me just zoom. Okay, just to make it small. So first I'll be drawing these expressions. So we have a resistor as well as inductor. So first resistor is resistor, which is quite simple, followed by one voltage source for the self-inductance, mutual inductance, and input. So this is for this coil. Here also we have self, mutual, followed by resistance. So first we'll draw with the easy ones. So resistor is 5 ohm, fine. This is I1 of S, fine. This is I2 of S, Fine. Resistor is 5 ohm. Fine. And what is the voltage? 20 in S domain?
So 20 by S.
20 by S. Yes, you are right. So 20 by S. First, we'll start with L. So we realized that whichever terminal that it is entering, that is plus for the self-inductance. So I'll use the same thing. So if it is entering this terminal, so this is plus, this is minus. And what will be the value? The value of the voltage source is current into S, because now we are in the Laplace domain. I into S into L. So I is I1S, right? I1S into S into 4.9. So this is 4.9 S into I1 of S. So did you understand that point, how we are getting this voltage source? This is very
Yes, sir.
crucial.
Yes, sir. V
Okay.
is equal to L by dt, then we can convert in Laplace domain.
Yes, Laplace domain. Yes, you are right. Now, if you see here, the current is entering the dot, and here the current is leaving the dot. So it will fall in the second category. So this is our first category. When the polarity are same, it is the first category or case one. In the second category, one is entering, one is leaving. So the polarity of M will be opposite. So this is plus minus, right? So now it is minus plus. And what will be its voltage? Voltage here it is 4.9 as I1, right? So now for mutual inductance, what will be the voltage value?
So 1.4 I2S S.
Yes, you are right. Because now mutual inductance will have M di2 by dt. So it is the other circuit or other branch current. So it will be 1.4 S I2 of S. Yes, you are right. And similarly here, which terminal the current is entering, that will be positive. So this is positive, this is minus. If we go back to our previous, here if you see, current is entering here, so this is plus, this is minus. uh, Sorry, this one, so this is plus, this is minus, and mutual inductance is just the opposite. So if this is plus, this is minus, mutual inductance is minus plus, because the polarity is opposite. So here it will be self inductance 0.4 S into I2 of S. Now can you tell me for the mutual inductance part, what will be the voltage source?
Sir, 1.4 S I1 S.
Yes, you are right. So 1.4 is I1 of S. So this is the most difficult part of this problem, drawing these voltage sources and converting them into S domain. So now once we have done, it is very simple. We just have to get the algebraic equations. So now I'll get two equations, one equation from this part and another equation from that part. So if we write the equation, I will get 20 by S plus. So from here I'll be going. So 20 by S minus 5 I1S minus 4.9 S I1S plus 1.4 S I2S is equals to 0. So this is my equation 1 coming from this circuit. Okay. Now I'll get equation 2 coming from the other circuit. So I'll start from here and I'll do apply KVL. So first is decrement. So minus 0.4 S I2 of S plus 1.4 S I1 of S minus 5 into I2 of S is equals to 0. So this is my equation 2, which I'm getting from here. So two equations, two unknowns, we have to solve. First, I can get I1 of S from here. So from this equation, I can get I1 of S is nothing but 0.4 S plus 5 by 1.4 S into I2 of S. Simple. We are just getting I1 of S in terms of I2 of S, so that it can be substituted in the equation 1, and equation 1 will be just in terms of I2 of S. So until this point, is this clear?
Yes, sir.
Okay. So now I'll just skip few terms because this is just mathematical manipulation. If you substitute I1 of s in this, and if you solve for I2 of s, I2 of s term will be coming something like this. So I'm just skipping for the sake of time so that I can discuss the overall solution. This mathematical calculation you can do later also. So it will be I2 of s is 28 by 25 plus 26.5 s. So it will be something like this. You can also check later. So every time you have to keep one thing in mind, that in our inverse Laplace transform table, always the coefficient of s is 1. So it is always 1. So what we have to do, we have to divide it by 26.5 in the numerator as well as denominator. So sorry, divided by 26.5 in the numerator as well as denominator. So now after doing that, you will get 1.056 by s plus 0.9433. So you'll be getting something like this. Now we'll apply inverse Laplace transform, which is our third step. So apply inverse Laplace transform. So what will be I2 of t? Anyone? I2 of t from this. So it is in which term? Some constant by s plus a. So constant by s plus a. So I'll go to my table. What is 1 by s plus a? So it is in this format, right? For plus here, it will be minus here. For minus here, it will be plus here. So now can you tell me what is I2 of t?
I took 1.056 into e to the power, sir, minus 0.940.
9433 t. Yes, you are right. Into u of t amperes. Yes, you are right. So I got my I2 of t. Okay. I'll just check with the answers. So this is first I'm calculating IT. So I'll know A2, B2. So A2 is 0, we have only B2. So my A2 is 0 and B2 we have how much? 0, 1.056. So it is within that range 1.056. And yeah, tau part will come later. So A2, B2 are fine. Now we'll go to I1 of T, which needs A1 as well as B1. Okay. So this is my I2 of t, and this is fine. So for I1 of t, what we need to do, you need to substitute this I2 of t, or sorry, I2 of s in this I1 of s, and again you have to simplify and see what term we are getting. Again, I will not be going into that mathematical uh, all the details now. I'll just simply write the I1 of s term that I'm getting. So I1 of s, you will be getting something like this. So I1 of s calculations are a bit lengthy. So I'll just show what you'll be getting. So it will be 0.3017 s plus 3.7714 by s into s plus 0.9433. Again, there was some constant in the denominator. Like coefficient of s square is not 1. So I have divided by that coefficient to make sure it is 1. Now it can be partial fractions. We can use a by s plus b by s plus 0.9433. So now if you apply partial fractions and calculate for or solve for a and b, you will be getting a is how much I was getting 3.998 and b is minus 3.696. So my I1 of s, my I1 of s is nothing but 3.998 by S minus 3.696 by S plus 0.9433. Now, if you calculate just like how we have done it here, apply inverse Laplace transform, which is our step 3. Apply inverse Laplace transform. What we'll be getting? I1 of t. There are two
So
terms.
3.998 plus, no, sorry, 3.998 minus 3.698 e to the power minus 0.9433.
94332 into u of t. Yes, you are right. So this is my I1 of t. The units is of course amperes. So if you want amperes. Okay, we have that I1 of t as well as I2 of t expression. Now I'll check I1, A1 coefficient, how much we are getting? 3.998, so close to 4. It is within the range. And B1 we are getting minus 3.696, so minus 3.7. It is also within the range. If you see, tau is minus t by tau. So let me just take this control C, control V. So these are the solutions we are getting. So now what is tau? So this is the question. Minus t by tau. So from there, what is tau?
So inverse of
Yes, yes,
0.9433.
yes, you are right. Inverse of this one. So you can check and calculate. It is coming around 1.06.
Yes, sir.
So my tau is 1.06, and now I'll check the answer. So tau is 1.06. So what is the value of tau in millisecond?
Mhm.
Tau value is 1.06. What is the value in millisecond? So for
Sir,
millisecond,
1060.
yes, yes. So for millisecond, we'll multiply it by in millisecond. We'll multiply by 1000. So tau is 1060. 1060, you are right. So we are getting something like that. And we can go and see this 1060 which is within this range. So similarly, we'll be not getting time today. So this is similar to our problem number 2, or here this first problem, where you will replace the capacitor with capacitor C and initial condition and apply KVL KCL, and you will be getting something like this. Yeah, that is for today. Okay, let me just summarize what we have discussed today. So today we have started with the advantages of Laplace transform. Mainly there are two advantages. One is there are no differential equation. Everything is just algebraic equation, and also both tangent and steady state solution can be obtained at a time. Because we are getting the overall solution considering the initial condition. First, we have discussed the S domain equivalent of RLC without any initial condition, followed by with initial condition. So we have to consider a current source in the case of inductor, or a voltage source in the case of capacitor, the polarity or the direction of the current or the polarity of the voltage is very much important. So that part needs to be taken care when you're selecting this. And R is R, L is SL, C is 1 by SC. Followed by one problem, we have replaced the capacitor with normal capacitor as well as the voltage source, and we have just applied KVL KCL here in this case KVL to get I of S. Then using partial fractions, we have like divided this into two different fractions, and using the inverse Laplace transform formula or the results, we have obtained the solution. And all these analysis, superposition theorem, Thevenin's theorem, Norton's theorem, everything can be applied. And in the in the Laplace domain also, there is no such like uh, rule that this cannot be that cannot be applied. Everything can be applied. There is no such restriction. Then we have seen the Laplace transform table uh, for different functions and what are the Laplace transforms. You have to remember all these things because these should be in handy. So every time there is some transfer function or Laplace transform, in this case, we can directly apply inverse Laplace transform only if you remember this. So these are the majority of the things that will be needed for this course. So I have written all those things so that you can also look at this and you can solve any problem. So first problem, we have considered this kind of network with capacitor having some initial condition. We have replaced it and then we have applied KVL. First, we have simplified this network into this network. We have applied KVL to get I of S. Then we have calculated I1 of S, I2 of S, and then we have correlated with our table and applied inverse Laplace transform to get I1 of t. Similarly, I2 of t, but here I2 of t is a bit complicated. We have converted done some mathematical manipulation to get I2 of t. Similarly, VC of S is uh, take a note, VC of S is not just across the capacitor, but across the capacitor plus the voltage source. So here it is Z into I of S. We have done the same thing and applied inverse Laplace transform by some mathematical manipulation to get VC of t. The second problem, which is a bit tricky, so it has two concepts. One concept is the mutual inductance concept, polarity, all those things, and the second thing is whatever we have learned today. So using whatever we have learned in the last week, the polarity, how whether it is same polarity, opposite polarity. First, we have drawn everything like the circuit, including the S domain. So once the circuit is obtained, we have got two equations, two unknowns. So first I have calculated I1 of S in terms of I2 of S. Then I have applied inverse Laplace transform and substituted this in the equation one, applied inverse Laplace transform to get I2 of S, similarly I1 of S. And then I have got all the constants. Yeah, so that is for today. If you have any questions, you can ask, else we can end this session. Also, there is less than a minute, so there is any chance that this might end. If you have no questions, then we can end this session.
Sir, source transform is also applicable in S domain, sir?
Source,
Source
yes, it is
transformation.
applicable, yes.
Okay, sir.
Yes.
Thank you, sir.
Okay. Okay, then all the best for your assignment. See you in the next week. Bye.